So this is Todd Danielson, the editorial director of Informed Infrastructure Magazine. Now I'm here with Seth Guthrie and Geoff McDonald. Why don't you guys introduce yourselves and briefly summarize your education and professional backgrounds?
Yeah, so my name is Geoff McDonald. I'm the senior product manager for Saks. I've been with Bentley for about 10 years now. Before that, I worked in the offshore structural industry. I got my degree from Texas A&M and my master's degree from UT, both in structural engineering.
And I'm Seth Guthrie. I'm now the product manager for ADINA and RAM Structural System, and I'm the director for all of our structural products. But my background is actually in technical support. So if people recognize my face or my name, it's probably from those years of RAM technical support that I've done. I went to the University of Kansas and came out to California to work for RAM at the time in 1999. And then, of course, Bentley acquired RAM back in 2006. So I've been with the company ever since.
All right, it's great for background. Can you guys give a little bit more specific about what your roles are at Bentley Systems currently? What do you do specifically?
Yeah, so as I said, I was senior product manager for Saks. Product management is a lot of jack of all trades. My background is application engineer, so usually dealing with customers, working with the product, coming up with solutions, or also helping out with the sales team to give people information about the product and some technical support, things like that. And product management, I think application engineering leads into that pretty well. There's some additional responsibilities in helping to set the vision for the product, working with our users on what they want to see next in Saks, and helping execute that plan from individual release.
Yeah, I would say that a lot of the work is setting roadmaps to understand the vision of a product. But as the director of all the structural products, I want to look at how they work together, how they make both products more powerful by collaboration, and to make sure that we can release products in a timely manner with features that users actually want. So we spend a fair bit of time talking to our users in informal interviews like this to understand what their needs are and make sure that we're developing the right products.
All right, great. So one of the things we're here to talk about is Bentley's offshore structural products. Can you describe what are they, who uses them for what applications, and how can they be used with ADINA? We're going to need a brief description of ADINA, please.
Yeah, I was going to describe Saks and Moses first, if that's okay, our offshore structural products, just to give a brief introduction. So we have two products in the offshore structural product line. We have Saks, which is our offshore structural analysis product. That's for fixed leg structures. It's been used in the offshore industry for about 50 years now, since the very beginning of offshore oil and gas industry. And it's used for in-place analyses, operational analyses, and even accidental analyses. And it's been started out in Louisiana, but it's used globally. So anywhere from the United States all the way to Japan, it's used across the world. Then we have Moses, which is our hydrodynamic analysis product. And that's for doing hydrodynamic analyses of floating systems. And you can do that for operations analyses or in-place analyses. And you can do the hydrodynamic analysis, and then it'll map the pressures and loads to the structure for doing structural analysis. So there's a complementary behavior between the two products, and we are continuing to integrate those together. But typically, the way I break it down is if it's floating, it's Moses, and if it's fixed, it's Saks. And that's really the easiest way to think about the two.
And when it comes to users, Geoff, right, you get a mix of structural engineers, sometimes mechanical engineers, or naval architects even, right?
Right. Yeah. Naval architects mostly work with Moses with floating systems, but yes, most people would describe themselves as an offshore structural engineer, like kind of differentiate themselves from onshore structural engineers because we use different codes and different structural, configurations, and it does feel like a different world sometimes. But yeah, their background would mostly be civil engineering or mechanical engineering.
And ADINA is a little similar in that ADINA is another product that's been around on the market for a very long time. It was originated by Professor Jürgen Bate, who is kind of one of the founders of the finite element method, and he's written a book that a lot of people will recognize on the finite element method. And he started developing this while he worked at MIT, teaching this topic to the next generation of engineers and developers. In fact, there's a little interesting story that one of the guys that started RAM Concept, another one of our products, took a class from Dr. Bate at MIT, and that's how he was introduced into this topic. So it's a close-knit group. ADINA had been known outside of academia as a tool to use in mechanical engineering. So it has a lot of solid-based finite element analysis, which is great for designing motors, engines, and that kind of thing. But it was also used in civil engineering for dams and bridges and other aspects. ADINA, at its core, does analysis which is dynamic. And so that's where we felt like it was going to fit nicely in with the rest of our products. And we'll talk a little bit more about how SACS and ADINA work together in a minute. But I'll just say that it has a really powerful and excellent solver for both implicit and explicit nonlinear dynamic analysis. Some of the things that we do particularly well are solve problems involving frictional contact or plastic material behavior. We even have rubber models that get used a lot in the mechanical engineering market.
These are all products used for offshore structures, right? So they would be using separate, to get the geology and the water analysis. Is that correct?
The main use cases for Moses typically are in the operation. So, imagine you're building a jacket structure on the shore, right? You need to fabricate it there because you can't build it in the water. You're going to load it out onto a vessel and then tow it out to the installation site. And you would use Moses to analyze the hydrodynamic motions of the vessel in transit, make sure that you don't encounter any stresses that are too large for the structure, make sure that the vessel doesn't tip over and sink to the bottom of the ocean, and things like that. And SACS, would be used for the structural analysis of that jacket as well, especially in place once it's fixed to the ground, looking at the wave loads on the structure, looking at the nonlinear behavior of the soils and the foundation, and looking at gravity loads and things like that. So a lot of the operations analyses of the fixed in place structure would be handled by something like SACS.
Yeah. And ADINA to date would not have been used very much in the offshore structural engineering world. And that's why we're interested in talking about some of the capabilities today where it might fit in, because ADINA's market has tended to be more in, like I said, mechanical engineering or maybe bridge design.
For someone doing offshore drilling, there would be a separate group that would be, the geologists and that kind of hydrodynamic software to find what they're looking to drill for or explore. And then when they have to create the structures, that's when they bring in the products you've been talking about. Is that correct?
We have more products within Bentley too. We have Plaxis and Leapfrog and great software for the evaluation of soil behaviors or the measuring of soil conditions.
Right.
That could be a whole other excellent webinar.
Yeah, there's a whole field dedicated to the geotechnical, subspace and looking at how to do sonar or other types of, non-destructive, methods to sample the soil, get information about the subsurface conditions and even the location of oil and gas and other, deposits. So that's a whole separate thing. Usually, where the gas is by the time you're involving our products, because we're at the point where we're installing a platform to either drill or extract those resources from the ground.
There is a little bit of an intersection with the suction buckets, right, Geoff?
Mm-hmm.
I don't know if you'd want to say anything more about how that works.
Yeah, well, so yeah, traditional jacket structures, they behave like a template. So you have a truss structure. I kind of think of them as similar to maybe like an electrical tower that you see, driving by, it's a truss structure, right? But we call it a jacket or template because you actually drive piles through those legs into the soil. And that's the traditional installation method. And we have very prescribed ways in which we can analyze that type of foundation. But when it comes to other non-standard types of foundations like gravity-based systems or suction bucket systems, the traditional methods to analyze those structures don't really apply anymore. So we have another product called Plaxis It's a 3D finite element analysis tool specifically dedicated to analyzing and modeling geotechnical behavior. And so we've introduced an integration where you can model a section bucket in SACS, export it to Plaxis, do the nonlinear soil interactions, and then export those behaviors back into SACS for an integrated analysis. So there's some overlap there where, where you start getting into these more niche type applications. You need to start integrating with these other more advanced analysis tools to be able to model that type of behavior. Very similar type of system we're talking about with ADINA here today.
Okay, thanks for the clarification and some more background. But we are here to talk about the structures that are being designed on these things. And one of the terms I run into is something called performance-based design. Could you describe what that is and why it's important in engineering, particularly with dynamic loads?
I think that performance-based design is getting used a lot more. People are taking a greater interest. It could mean a lot of things. We tend to think of it as you're trying to design a structure to meet some specific performance criteria. Usually it's a drift limitation or something that would be more stringent than the code-based strength limitations that are effectively about the yielding of your material. So there's been a lot of evolution. Codes like ASCE 41, I think I happen to have it right there, is giving you lots of different analysis options, and that would still allow you to conform to performance-based design. Some of those are what we tend to think of as advanced analysis solutions, and some of them are actually pretty straightforward. There's linear static analysis, which we all do pretty much every day with our software. There's linear time history, which some of the software can do and some can't. But then there's nonlinear material behaviors and nonlinear dynamic analysis options that are also available to you in those codes. And we find that they give you potentially the most realistic simulation of your structure, the most accurate way to evaluate its performance. And sometimes that might give you greater confidence in the structure you're designing, or it allows you to possibly save some money by designing a slightly more efficient structure that's still safe.
Okay, that's great. And you touched a little bit on, you mentioned the nonlinear analysis. So could you just a little bit more about what that is and why that's important to engineers?
Well, of course, the main thing that we think about is material behavior. We tend to treat steel and concrete material as if it is linear. It deflects a certain amount under a certain amount of load. It has a constant stress strain curve until it gets to yield. But once it goes beyond yield, it starts to become plastic, and then the deformation is much greater with just a little bit more stress. And most software doesn't conveniently handle that because we're usually trying to design things that are in the elastic range. But with, say, a seismic structure where you intentionally put an RBS into your beam where you want it to yield, to do a full analysis of that and to understand how it might behave under a severe earthquake, we can now simulate that with ADINA, see where it goes into a plastic behavior and you have permanent deformations, and confirm that the overall drift of the building is still within your range, and that nothing else fails besides this dedicated zone.
So how does all of this fit specifically into the offshore industry? How are these things that we've talked about kind of fit more specifically into the offshore industry and what they're trying to accomplish?
Well, of course, within the offshore industry, you have, just your normal design code checks. You have an operating load. You want to ensure that whatever stresses that occur in your structure don't exceed some sort of limit, right? And that's kind of your traditional design code. We use different design codes, but ultimately they boil down to very similar types of applications that you would see onshore. But beyond that, we typically look at accidental or extreme events where things can either go up to their limit state or maybe exceed it slightly. And even those, we have some design code, but a lot of times we'll look beyond that and say, okay, for instance, like for an operating condition, we'll have a hurricane that hits the structure. We have our operating wave, we'll have an extreme wave, and then we'll have the accident level wave that comes. And when we design things, we typically design things to be up to a certain level, and then a lot of times we're interested in what happens beyond that level. What is the performance of the structure when we encounter these accident level events, and can we ensure the safety of the personnel on the platform, make sure that they have enough time or resilience of the structure to get off the platform safely, and to ensure that the structure doesn't collapse into the water. So these types of things we look at are performance-based designs. So it's this is what we call a pushover analysis. We take an extreme level event, a storm, 100-year storm, and then we increase that load on a structure we model the nonlinear behavior of the structure and take it until it collapses. And we get something called a reserve strength ratio, which gives us the ratio of the structure performance against that design code check, right? So that's a way that we can look at the performance of the structure. And like Seth was saying, get a level of confidence about the structure based on that value that we can arrive at.
Yeah. Yeah, in a way, I feel like the offshore industry has been doing performance-based design longer than we have in the building sector.
Yeah.
For the most part, building design codes have been lagging behind. We were designing to service level limit states on wind and seismic until not too long ago. We've only, in the last 20 years, started switching towards designing for 30 or 100-year events, like Geoff is saying.
And I mean, I think part of that is because the offshore industry, we are designing structures in very extreme, remote areas where that is really important. You can't just, say, well, okay, the wave's never going to hit it. We do see these types of environments all the time. Other types of analyses that we look at for performance-based design are things like blast, dropped object, or ship impact. Those are things like where a blast analysis is where you have a pressure wave from an explosion. You have something like a firewall that you're looking at. You want to ensure that that firewall can withstand that blast, protect personnel on the other side of that thing. So you, again, look at the nonlinear behavior of that, make sure that that is going to behave. Obviously, in that type of environment, you're not expecting that thing to remain elastic. It is going to be nonlinear, and it's a highly dynamic event. So you have to be able to account for both of those types of influences on the behavior of the structure.
And it's interesting because SACS is already doing nonlinear analysis. It's not like ADINA is totally new in the offshore market, or nonlinear analysis for that matter. But we feel like there are certain things that the methods in ADINA will make it even better for our users, and fill in the gaps at the most advanced level of nonlinear behavior.
Do you think these things you talked about, like being prepared for 100-year storms and ship impact, now it seems like these storms are becoming, 50-year storms, 20-year storms, and we recently did have a ship impact. Will these kind of products be more commonly used in all types of designs as these things become more common?
I do think that there is a tendency to do these more advanced analysis options. People might have been hesitant in the past, either because of a lack of expertise or by the cost of the software or the difficulty to learn the software. At Bentley, we're looking at doing several things to make the cost problem less by bundling it with some of our top level SACS and structural products. And then we're doing integration of the products so you don't have to completely start over, right? The other thing that you'll see, I do suspect, is the reevaluation of existing buildings for new levels of loading. In fact, I did a webinar just last week that was based on a building in Turkey where it was deemed not up to the current code and it needed to be retrofit. And in order to retrofit, they were looking at various options, whether it be adding extra walls, or what they ended up doing in this case was adding dampeners. And so we were able to show how ADINA, you could model those dampers and accurately predict the seismic behavior and the improved performance for an existing structure. And of course, that happens in the offshore structure too.
It happens all the time. I mean, we look at a lot of these structures that have 20, 25-year design lives that are still in the water, extending that life, right? Extending that life in environments that have actually become more hazardous. We see that when those structures were when those structures were initially designed, they were had a certain 100-year event. And as we've collected data over the years, we've seen that those 100-year events are actually becoming more extreme. So we've actually changed those hazard curves. So not only is that structure being, trying to extend the life past when it was designed, you're trying to design it in a more extreme environment, and you might be modifying the structure to add new types of equipment, add extensions, things like that you did not initially design for. And I find that performance-based design might be your only option in some of these scenarios, like dampers, where your standard design code checks don't cover that type of behavior. They're really, your only option is to look at a performance-based design philosophy.
There's even a case or two, right, Geoff, where existing topsides were sort of modified to support wind turbines?
They're looking at that right now. That's part of an ongoing project in the Gulf of Mexico, is trying to either use them as wind turbine platforms or as tieback platforms for the high voltage cables. So yeah, there's an opportunity there to even extend the life beyond what we would even expect for the reserve that is there. So yeah, very interesting work. But all of that stuff is, something where you really have to start sharpening your pencil when you look at this thing.
Okay, thanks. That's great. So one of the main things I want to talk about in just a little bit is this really interesting competition that happened in 2023. But I want to make sure that everyone listening is up to speed on ADINA and how it's used before we get to that. So can you tell me a little bit more about how ADINA does help offshore structural engineers solve the problems we've been talking about?
One of the things that we were talking about was blast analysis, for example. There's a couple of different ways you could handle blast analysis by applying a varying pressure wave. You could also do it using computational fluid dynamics, or CFD. It's hard to say, so everybody says CFD. ADINA includes a CFD analysis module where you can use fluid. The fluid gets meshed like the structure, and then you can apply some of these other concepts, which would be a more accurate representation of the actual pressure wave that comes from a large blast. Ship impact is probably another one. Geoff, you want to say anything more about that?
Yeah, I mean, so we have methods in SACS to, like Seth was saying, to analyze these types of kind of simulations, right? But in SACS, we're limited. We do very well at dynamic analyses, where you can do a linear dynamic analysis. We do very well at static nonlinear analyses. But when you approach these types of dynamic nonlinear problems, this is where the nonlinear material behavior influences the dynamic behavior of the structure. This is where ADINA can really add a lot of value, because we can model that interaction in ADINA where it's not very easy to do that in SACS. So things like ship impact analyses, obviously it's a dynamic event. Blast analysis, highly dynamic event. But along with material nonlinearity, these are types of things that we can model in ADINA, where we can truly get a much better, much more accurate sense of the behavior of that event.
All right, great. Let's move on to this competition that was very exciting and interesting. So now at least Seth was involved in this competition to predict the dynamic shake table response to a 3-story, 40-ton reinforced concrete U-shaped wall. Now, can you explain the significance of this competition and why you think the team organized by DeSimone Consulting Engineering, with members from academia and Bentley Systems, won this prize?
Yeah, this whole experience was really good for me. I think it's good for the industry too. My connection with DeSimone actually came from just a contact. Somebody who was working on the ADINA team knew somebody who worked at DeSimone. DeSimone didn't know anything about ADINA, but they used some of our products. Specifically, they used some RAM concept and some RAM structural system. And so they're actively participating in these kinds of blind prediction studies to demonstrate their expertise as engineering practitioners. They collaborate with a couple of different professors from academia that all contribute some different ideas. And we decided that we would make a composite team. my contact Geoff at DSimone would submit the entry. They would produce one entry using OpenSeas, which is free software, to do some finite element analysis. And we would similarly do another exercise using ADINA. And one of the reasons why this worked out so well was that we were sort of reality checking each other. If one of us made a drastic mistake in our input, it would show up because our results would be radically different from the other teams. And so we worked on these two, continuing to refine the models to get the concrete behavior to be more accurate. And in the end, what we did with ADINA was we modeled at least one story of this. It's an elevator core. It's a C-shaped or a U-shaped wall group, 3 stories tall, that was subject to an earthquake with a lot of twist. And it was actually subjected to 7 different earthquake spectrums, or maybe 8. And our job was to figure out what was its period, how would it displace, and how would it ultimately fail. And so several of the competition teams, including teams from all over the world that used various software to do this, several of them predicted the right kind of failure, or they predicted a pretty good period response or deflection response. But ultimately, the ADINA model, which did a very detailed analysis of the concrete down to modeling of the bricks and the rebar separately, it had the best overall. So we got the right failure mode, we had the very accurate periods, and some good deflection calculations as well. But it was a great experience working with a cross-functional team like that.
How long did this competition take place? Is this something that, like,
They sent out the request for submittals, and they always give you some time for these things because they know it's everybody's second job. And I think we worked on it for maybe 5 months, periodically meeting as a team, and then submitted our predictions. Then they did the actual test, which was quite an event. They had, you can imagine, a very large room in order to break this wall. What they actually built was half size, by the way, but that's still a very tall wall to shake to death. And then the awards were presented at the World Earthquake Conference in Milan. So that was actually just in this summer. The work started in 2023, but it extended into this year. So it still feels quite recent.
okay, so it's a long-term process, but a lot of it is doing the back work and turning in the teams. Like, how many teams were involved in this?
I think there were 22 to 24 submittals. We had 3 submittals within the DSimone group. So there was at least a dozen or more teams involved.
Okay, and a lot of that's done behind the scenes, and then the shake table part is kind of the big dramatic
Yeah,
moment.
similar exercises done at universities over here. University of California, San Diego does some of these kinds of tests occasionally. But this was one of the largest scale ones we'd seen. They had actually done a similar test of a wall like this in the past, but they had only done it for some like linear loading. And so now they wanted to shake it and take it to the next level. And ultimately, the research goes into papers. That research will hopefully affect design guides and eventually codes, and give engineers the freedom to use some of these methods to demonstrate the safety of their structures they're designing.
Okay, so do these competitions happen because without them, people wouldn't have put the resources and the time into finding out whether how good their modeling actually works, and
Yeah,
this is
that's
a way to
it's a
kind
big
of
part of
force
it.
people to challenge themselves in a very difficult situation, and then not only do you see how good you're doing, but you can learn from it and create better products on the backside.
Yeah, I think that's all those things feed into it. Um, one of the ways we learn as engineers is when something fails. Um, there are disasters that are always terrible, but we often learn a valuable lesson from those disasters. Everything from the Hyatt Regency Bridge collapse to more recent cases. But it's very difficult at the end, after something's happened, to piece it together. With a controlled test like this, just like a controlled experiment in the medical lab, you can monitor the strains very accurately, or any other sort of measure that you want. And at the end very exactly. They could also do core samples, and they would know exactly how strong that concrete was, and you're taking out a lot of the variables. And so if you can ultimately demonstrate that there is a method of analysis that is effective at predicting how it will behave, then that should be an applicable method for people to use in designing new structures.
The way that we get to a lot of these more prescriptive type of design methods is through these types of work, where you actually have to fully understand the behavior of these systems using more accurate performance-based analysis methods to be able to state, confidently that if you do these rule of thumb type analyses, you will be able to design it this way. So
Yeah.
this is where it starts. This is where you can get to those more prescriptive methods.
Yeah, pretty much everything in the code started at one point as a research exercise for somebody.
Yeah.
Yeah, I think most things I see like in actual academic research labs at universities. So I think it's kind of cool that you can branch out and reach, these businesses creating these products and get their best people working on it too.
Yeah, I wish I could have attended the actual event, though I would have wanted earplugs because I heard it was very loud when that concrete finally spalled. What happened is the rebar near the tips of the sea buckled and the concrete exploded.
We talked about the software that was used. So how was ADINA in particular used to make the winning prediction? Was there any other software used? And can you describe the software and I guess the modeling is about as detailed as you can if you feel like it needs a little more discussion.
I know that OpenSeas was used because we did that within our team, and I know ADINA was used. I'm not sure exactly what other software was used, but I believe that some of the other sort of classic products that you would see, like SAP 2000 or STAD or some other products were used that would do a general purpose finite element analysis. In OpenSeas, the way you would model a wall sometimes is with a series of linear elements, what we call like fibers. And that way you can start to simulate the behavior of a wall with a whole bunch of sticks. And then some of those sticks could yield and become plastic. And it's a pretty accurate analysis. It's what a lot of advanced software does to handle the evaluation of a wall. But we're sitting here on top of ADINA, a product that's been used in mechanical engineering to model solids for ages, a product that has pretty advanced meshing capabilities, and a product that can easily handle any kind of time-lapse loading you want to do. So we decided to take the approach of modeling it, as close to reality as we could, using three-dimensional blocks for the concrete and one-dimensional trusses that are linked to those blocks at series of nodes in the exact place that the rebar is. So that composite modeling of the system was, from a stiffness point of view, very accurate. And then what we did to get a little bit faster run and some better performance was we decided to take that super refined modeling only in the first story, where obviously the failures were going to occur and the greatest strains were going to take place. And then above that, we used simplified analysis. We used shell elements for the top two stories. And so we kind of had the best of both worlds, a model that would run in hours and not days, yet a model that had a great degree of precision where you needed it.
Okay, so it's obvious that these competitions bring people together, so you're getting a variety of specific outlooks and inputs of these teams thinking together to make these decisions. But how do these competitions create real world benefits and more sustainable structures? How does it translate into not just the better software, but to the better structures that are going to come from them?
Yeah, in this case, we're talking about a concrete structure, and you can see how this might impact the way seismic provisions are designed for many buildings that people live in around the world. There are other examples. I think concrete is a particularly difficult material to understand. It has an inheritively nonlinear behavior. It can take compression but not tension. But even steel structures, a lot of steel structures, the methods that we used for analysis and design that we all use today have come from these kinds of research projects. Geoff, were you thinking of anything in particular where research might have helped to develop an idea?
Oh, I mean, everywhere. Research is critical to furthering our understanding of these complex problems. I would say more specifically when it comes to nonlinear dynamic analyses and using these, one thing that we found in the offshore industry is that when we're looking at dynamic systems, um, a lot of people in the structural engineering world think in terms of linear systems and conservatism when it comes to linear systems. And that can be a pitfall for people when they start to think about dynamics, because typically when you're trying to make a system more conservative from a linear standpoint, you make it stiffer, right? Um, that changes your dynamic behavior. And that may not necessarily result in a more conservative result in your dynamic results. So we've seen offshore industry where we've had failures, real world failures, because the dynamic behavior of the structure was wrong because they were making conservative assumptions about the stiffness or the nonlinear behavior of their system, right? They were trying to be conservative. And so I think using nonlinear dynamic analyses can avoid those pitfalls of trying to falling into that conservative mindset. Sometimes when you're being conservative, you're not actually being conservative. The right thing is not to be conservative, but it's to be accurate.
Yeah.
Look at this in the actual behavior. If you really see a dynamic nonlinear system, analyze it as one. Don't rely upon a simplification for a linear system. So I think this is where we can really contribute in the space to improving, making that more accessible to people to be able to do those types of analyses and not rely upon those simplifications.
I know in the building industry, there was a flood of different proprietary seismic connections that have come out, or even seismic braces that have come out in the last couple of decades. And these are specifically designed to be very strong, yet they can become plastic and dissipate energy where they need to. There's side plate, there's Durafuse, there's traditional RBS connections, and then with braces, you've got core brace and the yield link, just to name a few. And each one of those kinds of things needed to be developed and tested, and they did rely a lot on physical testing to demonstrate that the connection can achieve a certain amount of rotation without failing. It can dissipate a certain amount of energy. And well, ADINA, or a product that can handle nonlinear plastic behavior, can be used in conjunction with that, so that when you get around to finally physically testing, you're pretty sure how it's going to behave. And you only have to test a couple of cases and not so many, because destructive testing is very expensive. And in the end, it's good for everybody, because we have these seismic systems now that are rated. And when you have a big seismic load in California, nobody even worries about it like they do in other countries where they have less resilient structures.
When you talk about being, too conservative, is that in terms of like the codes that are being used because they're kind of devised to be the absolute minimum standard? When if you've got these like real world, highly complicated models, you can find out a little more exactly how things work and perhaps can even stretch the presumed codes and standards that are being used?
Yeah, so I like a really good, easy example is looking at our foundation. We take a look at the soil and we say, ooh, my soil is, between these parameters. I'm going to look at the low end of that because that's going to be conservative, right? When I apply a lateral load to the structure, if it's not as stiff, it's going to move more and it's going to fail earlier, right? But then when I go to the dynamics, making that soil soft like that will change the mode shapes, the dynamic behavior of the structure, so that um, when you look at dynamic responses, it's more important to look at the frequency of the loading in relation to the natural frequency of the structure. That's what's critical, not necessarily whether it's stiffer or softer. So you can look at a system and say, ooh, that's not being excited, right? But be missing it because you made an initial assumption that your soil was softer than it actually was. So those are the kinds of things where you can start falling into these pitfalls. And there's other things like that where you're assuming things are not as stiff as they are in the structure itself, right? So those types of things you have to be really careful about when you start looking at nonlinear dynamic behavior.
Yeah, I would say, another way to put it is that you're overestimating one thing at the consequence of another. So
Right.
you might overestimate your masses, but then you really didn't solve the right mode shapes because the actual masses were less. Or in the case of the braces we were talking about, you could oversize the brace and think you're conservative, but all you've done is you've made it fail at the connection, which is the worst thing you want to do. A softer brace that yields is better for the people inside.
Okay, that makes a lot of sense. I think we've got a great discussion of the competition, how that worked. But before we go, I've got some Bentley software experts here. Can you tell me a little bit more about ADINA and how it could be used in other types of applications, and what is special about it that has a broader use than what we've been discussing?
Yeah, it's like I was saying before, it was a product that was born in academia, so it can solve all kinds of problems. They're not necessarily the kind of things you do every day. We have RAM Structural System and STAAD Pro and SACS for those people that are designing the same kinds of structures all the time, and they're looking for software that is very specifically geared towards one task. ADINA is incredibly general purposed, and it can be used for everything from designing parachutes or engines to concrete dams or even electronics. So we see it used a lot in academia and in mechanical engineering, but we're hoping that structural engineers, whether it be in the form of a connection design or an occasionally unusual structure, maybe some curved steel, there's all sorts of applications where ADINA can help you and complement the other software that you use.
Yeah, looking at the offshore industry, I see a lot of opportunity. We have, like Seth was saying, our goal with Sachs is to make a product that solves the API design code, right? The ISO design code. Those are the offshore design codes that prescribe how you design a structure. But when you go beyond that, there's a lot of opportunity to use a general finite element analysis tool to look at these individual types of problems. We talked about some of those already with like ship impact, but even things like CFD. We talked briefly about CFD, but you can look at CFD for blast analyses. You can look at CFD for hydrodynamic interaction with the structure, right? I've seen this in the industry being used to look at wave run up on large caisson type structures. So there's lots of different interesting applications when you go beyond what's prescribed in the design code to look at this as a tool to be able to solve those types of problems.
Okay, that's great. I've just got one kind of question kind of for myself. I often read about, and then we talked a little bit today about finite element analysis, but I rarely see a concise and helpful description of what exactly finite element analysis is. Do either of you guys have a description that you're fond of and think might sum it up in a minute or so?
Ooh, that's a tough one.
I think that it's hard to come up with a concise answer because it's so broad. I mean, at the end of the day, these are small elements that represent some sort of interactive behavior, right? The finite element in them is the name, right? They have an element of a finite length or finite space that represents some sort of physical property, right? So that could be stiffness, that could be thermal conductivity, that could be a fluid flow, right? All these different types of things are finite elements.
Mm-hmm.
It's the mathematical representation of that system,
Yeah.
and broken down into these small, relatively easily to solve bits, right?
And those elements, whether they're one-dimensional things like truss elements, two-dimensional things like plates, or three-dimensional solids or fluids, they all enter into a big mathematical matrix. And the reason that finite element analysis is so popular today is that the problem you have to solve is to invert a really, really big matrix, which is hard for humans but easy for computers. And we have made some incredible advances in the speed of that, thanks in part to even the Intel sparse solver. So now problems that seem unimaginably complex can be solved with a computer. And then the engineer can look at that and understand in a macro way why it's behaving that way. Why is that thing twisting so much? Why is that thing cracking in this location? And with ADINA, we do a lot of animations to help you see and visualize exactly why that's happening.
So guys, those are all the prepared questions that I have. Do you feel like there's anything that we missed that you want to make sure that we touch on before we stop recording?
I will say that we'll be at the National Structural Engineers Association conference in Vegas next month. If anybody happens to hear this and want to say hi, I look forward to seeing you there.